Right, dear students, let us continue our discussion on electrostatic potential and capacitance. So today we will be entering the second part of the chapter, capacitance. So what is a capacitance or capacitor? Let us see what is a capacitor. Okay. Basically, it's a device, it's an electric device which is used to store charges. Okay. Now our intention is to store charge. But before we go for the particular device, we all know that any kind of surface, any kind of body can store charge in it, right? If it is non-conductor, we use methods like charging by friction and we get the charged body. And if it's a conductor, we use the methods like charging by conduction and charging by induction, and we get the charged bodies. Now, let us start with the concept that we know. So, say now I want to charge this body. I want to store charge in this body. So, we all know that how to charge this body. See, storing charge and charging both are one and the same. Okay, it's fine. But when we say storing charge, we are actually talking about bigger magnitudes, large amount of charge stored in it. Now I want to store good amount of charge in it, right? So first I'll think of choosing whether a conductor or non-conductor. What do you think of it? Should we go for a conductor or a non-conductor? Alright, if you go for a non-conductor, it would be difficult to store too much of charge in it, right? Because the device, the substance itself has got no additional charges. So it's difficult to store charge in it, and there is one more disadvantage you will get to know when we continue the discussion. So now the first part is removed. We are not going to consider or take non-conductors to store the charge. Okay. So what is left? It's conductors. And one more reason to not to use non-conductors is hardly you can only charge it by rubbing, right? Friction is the only method to charge a non-conductor. So how much you can rub? So that takes a lot of mechanical energy to rub and store charges in it, and there is plenty of charges of leakages and all. So it's fine. We are not considering non-conductors for now. Insulators are out of the consideration. We will be considering conductors now. Okay. So it's a conductor. Now, when it comes to conductors, I'll think of it whether to choose bulk conductor or hollow conductor, solid or hollow. So then from the electrostatic properties of the conductors, I get to know that anyhow, even if it is bulk or hollow, charges are going to always store or accumulate on the surface itself. No use of solid conductors, right? No need to worry. Anyhow, we don't be in need of solid part. Okay, this solid part inside is not of use for us. So I'll be going for hollow for now. Okay. Yeah, you can choose any hollow or even solid also fine. So during the discussion, we will also consider solid itself, but hollow is fine for me. Okay. So solid is also fine. Okay, you can store charge even in that. Okay. So now, how to charge this conductor? We have two methods as of current discussion. One, it's a conductor now. So one, I should make use of charging by conduction or charging by induction. Induction won't be that efficient, right? So I should bring already charged body close to it, and the charges inside it will get separated. One, I should connect the other end to the earth, so they will go to the earth. So we will get certain amount of charge, but that's not the most efficient method of charging. So comparatively, from conduction and induction, I will go for conduction itself. Okay, because I can charge it to. Finally, my intention is to charge the body to a higher value, higher amount of charge as much as possible. So that is why I will be going for conductor now. So now what I'll do, I'll bring charged conductor in contact with this body which I need to be charged. Then what happens? Few charges from this charged body will move or flow into this charged this body which has to be charged. Okay, few charges, either touch them directly or connect them using a wire. Anyhow, charges are going to flow into it, and hence few charges will be accumulated on the surface of the chosen conductor. Now you see, not all the charges from the body we are bringing will flow into the conductor, right? Because see, now we have clearer idea. We did not have this idea before. Since we know the concept of potential, see, considering this body which has to be brought, before it was brought in contact, it was charged. We all know that, right? This is the scenario of before bringing that into contact. So, when the charges get accumulated on surface of a material or a substance, it develops certain potential on its surface, right? We have discussed it. When charges are accumulated on the surface, it develops certain potential on it. So, certain potential, no need to worry about the magnitude, but it will be there. Okay. So, say V is the potential on the surface of this charged body chosen before it was brought in contact with the conductor or the body which we need to charge now, or we need to store charge in it. So, now what I do, V is the potential, and before charging this conductor had zero potential, no charge in it. So, on the surface it was 0, the potential was 0. Then I brought this, or I connected them using a metallic wire or a physical contact. Charges started to flow from this charged body to this metal body, just because there is less potential on this body and higher potential on this body. Following? So, V is the potential here and 0 is the potential here. There is potential difference. Following? There is potential difference, and where and all you have potential difference, there and all there will be flow of charges. So, charges will flow from this to this. Just like from say 2 tanks you have, one completely filled, the other completely empty. You connected them. The water from the filled tank will start to flow into the water to the water tank which was empty. So, now the water level starts to rise or fall down in the higher one and rise up in the empty one. So, this flow will continue till the water level balance in both the tanks. In the same way, the charges from the body will keep on flowing till both of them have got both of them develop a new potential, say V dash. Okay, be careful, it's not about the amount of charge flow. No need to, I mean, you shouldn't think like this body and this body will have equal amount of charge. No, it is not like so. Even when you have a small pipe and a filled tank, the water level in the pipe will rise till the height of water tank, right? Not the way, not in such a way that the equal amount of water will be there in both the pipe and the water tank. No, it's not like so. It's about height, the potential. So, when both of them attain equal potential, no potential difference, no flow of charge, right? So, there is no potential difference and no flow of charge. The flow stops. So, then we start to think, okay, what to do with this? How is this V dash dependent? So, on the surface of a charged conductor, the potential is given by V is equal to 1 by 4 pi epsilon naught Q by R, okay, where R is the radius of the sphere, right? You know that, right? It's similar to electric field on the surface, where Q is the total charge accumulated on the surface. Now, you see, V is inversely proportional to R, right? So, I can make the body bigger and bigger and bigger. So, if I have a bigger conductor, I can store more charge in it because V is inversely proportional to R. Following? And now what I'll think, okay, fine. If I have a smaller conductor, I can store certain amount of charge. If I bring a larger one, I can store large amount of charge, because you see, when R is increased, V is decreased, right? And we want lesser V. So you can accumulate, okay, now you remove the factor of V because we need to attain V dash. Now you see Q is directly proportional to R, right? Because V dash is the potential where the flow stops, where the charge exchange stops. So V dash is fixed, okay? And 1 by 4 pi epsilon naught is constant. So Q is directly proportional to R. You increase R, you store more charge in it. Following? So then what I do, instead of choosing a small sphere, I'll choose a bigger one. So the amount of charge that was stored in this comparatively will be lesser when we compare when we take a larger one or a bigger sphere, right? So now I can store more charge. But this is not a permanent solution to store the charge, right? This is fine, but not the permanent solution. This is like how large you can make, that is not this sensible one. So then we start to think of it in a different way. What we will do is, okay, instead of choosing a bigger one, okay, we will bring another charged body close to this, okay, but the kind of charge chosen with the other body will be the opposite of this. Means now say this is positively charged now. So now I will bring a negatively charged body close to this body whose where I need to store the charges. And now you see, due to the presence of this negative charge, there will be a negative potential developed at these points, right? You agree on that? Because at this point now we have potentials due to this very own potential of the conductor, this one, and say conductor A and the newly brought conductor B. So both the bodies will have their own influence. So this, if this is V dash, this will have some say minus V double dash, okay. I mean potential at this point due to this negative charged body brought closer will be due to this body and due to this body. So now you decrease the potential, right? So when you decrease the potential, now you can actually store more charge. Following? It is somewhat like you had a pit where you can store, or you can put mud in it, and you want to actually, okay, nobody stores mud, leave it. You want to store, say, what do we store in a pit? Say you want to store, okay, let me take stones, okay. I want to store stones in it. I have a pit. Now one way to store more stone in the pit is either you increase the size of the pit, make it broader, or you make it deeper, so decreasing the potential, right? So negative potential is brought closer to that, somewhat similar, not exactly, but it's quite simple, mathematical. So now at this point it is potential due to this minus potential due to this, so the potential decreased, so more charges can plunge in. So finally it will attain V dash to certain extent, after certain extent, so and then the stop will flow, but its ability to store charge has increased without making it a larger one. So this was fine, everything was good, but then who will bring this positively charged body every time to store charge in it? That's the difficult one, because I want to make this body charged, bringing a new charge, old charged body to make this charged, make this body charged. That's not sensible, right? So this doesn't seems to be the best method of charging a body. So then what we did, we looked at the phenomena and we removed this body which has to be brought. Then what we did, we actually connected these two metal spheres or these two metal bodies, okay, not exactly sphere. Sphere is the shape where you can store most charge, that is why we chose that. What we did, we connected them to a battery, okay. Now here comes, what's the purpose of connecting them to a battery? Battery is something which can move charges, right? DC it can do. When we connect that to battery, it can actually grab positive electrons from conductor A, and like this is positive end of the battery now. So the work of the battery itself is like pulling all the electrons from one end to and then pushing them to the other end. So it's pulling the electrons from this end, it will pull it and push them to this end, right? So this phenomena will continue till the potential difference between these two becomes equal to potential difference between the cells or potential of the cell chosen. So that continues fine. Now we have most efficient one, okay. I can't say most, more efficient compared to the last different methods that we chose. And then we think of something, okay, why do we need to choose this hollow or solid metal block? Choosing a block is not that good idea, right? So what we'll do, instead of choosing the metal block, it's anyhow the charges are stored on the surface of the conductor chosen, right? On the surface. So why to worry about the shape of the conductor? So let me choose the simplest shape, which is a parallel plate, okay. So we'll be choosing a parallel plate like this. So a parallel plate, why? Again, anyhow we need a plane surface, charges will be storing on the surface, the inner hollow part or the solid part is not of use for us. So let us make it more simple. So finally this was said to be the most efficient method of storing the charge, and this is called parallel plate capacitor, okay. Two parallel plates, two conducting parallel plates separated by a certain distance, which has the ability to store charges in it, can be considered as parallel plate capacitor. You will have the perfect definition in the reference, you can choose refer to that and remember that. Now more the potential difference between this and this plate, because when the charges accumulate on one of the ends, say this now will accumulate positive charge and this will accumulate negative charge. So due to the accumulation of positive charge here, it will develop certain potential plus V, okay. And due to the accumulation of negative charge here, say let me call this as plate A and plate B. So VA, they will be actually equal. Let me take this as minus VB because it is negatively charged. So the potential difference between these two plates is VA minus VB, right, which I can take it as delta V, or V is also fine, okay. V is equal to VA minus VB. To take delta V, V is fine. Where what is V here? V is the potential difference between plate A and plate B. Now as similar to the previous one, now we all know that more the potential difference, okay, more the potential difference, more the charge you can store in it. Following? Where does this potential difference come from? The potential difference comes from the battery that you connect. So larger the battery you can connect, more the charge you can store, obviously, right? So more the potential difference, more the charge you can store. Following? Now that gives us the idea that V is proportional to Q, where Q is the charge stored in each plate, which means obviously the charge stored in one of the plate is plus Q, the other plate will be minus q, and I am taking the magnitude of charge of either of the plate, which are normally equal, okay, plus q and minus q. And now I want to remove the proportionality. What do we do? As usual, we introduce a constant, right? So here the constant that I introduce will be called as C, which is capacitance of the given arrangement. So how does that C can be put there? So C can be seen as follows, but here it will be it won't be that good to take V proportional to Q. Let me consider Q proportional to V, right? Both are fine, but in order to introduce the constant, I don't want to put the constant in the denominator, right? That is why. And physically speaking, it's not it's Q which is dependent on V, right? Potential difference between the plates, which is V. Q is the charge stored in either of the plate. So Q proportional to V, right? Okay, this seems to be good. And now I want to remove the proportionality. So Q becomes equal to CV, where C is called the capacitance of the given capacitor. So this entire device is the capacitor, okay? Particularly this is parallel plate capacitor. Two parallel plates made up of conductor, which are used to store charges together as a system, can be considered as capacitor. Now this C is the capacitance of that capacitor. So what is capacitance now? Capacitance is the ability to store charge. Okay, I am telling you about the physical sense. So more the capacitance, more the ability to store charge in it. Like the volume of container that we choose, right? Just an analogical example. If you have a cup, you can store hardly 100 ml, 200 ml of water in it. If you have a jug, you can store till 1 liter. Or if you have a tank, you can store till 1000 liters. If you have a bigger tank, then you can store lakhs of kiloliters in it. And if you have a lake, there you can store more than that, right? So that is how its ability to store water in it, okay, that when it comes to those containers. Here its ability to store charges in them, right? This capacitance physically means. But when it comes to definition, we define it like so, mathematically like this. So C becomes equal to Q by V. It's the ratios. Capacitance of a capacitor is the ratio of charge accumulated on either of the plate, or magnitude of charge accumulated on either of the plate, plus Q or minus Q. We are worried about only Q now, magnitude of the charge. Magnitude of the charge, ratio of magnitude of the charge accumulated on either of the plate to the potential difference between the plates. See, it is the potential difference between the plates, right? So that is how we define C, the capacitance. And this capacitance has a unit, a SI unit given by, so you could say, sir, this is coulomb, this is volt, coulomb per volt. Yeah, that is fine. But a scientist's name is chosen for allotting the SI unit for this, which is represented by capital F and is called farad. Okay, farad. So from now on, the capacitance of a capacitor will be in farads: 1 farad, 2 farad, 3 farad, 5 farad, 10 farad, 15. Normally it's like microfarad, millifarad, nanofarad and all. Now we'll move ahead and see or derive an equation for this C. Okay, so this is see, now Q and V will not decide C. Okay, Q and V are actually proportional to each other, and C is the characteristic of the device chosen. Okay, it's the internal characteristic. So there should be some physical connection between the dimensions and physical conditions of the system and this C. Okay, we'll get to know what is that connection or the expression for C in terms of the physical dimensions or physical properties of the given capacitor. Okay, so now we'll derive an expression for C. Right. So the base expression that we'll be choosing is what we had, C is equal to Q by V. And now the expression of electric field due to these charge accumulated parallel plates will give us the connection will give us the advantage or the help to derive the expression for C. Okay. So here you have plus Q charge accumulated and here you have minus Q charge accumulated. Now due to this positive charge accumulated, there will be electric field like this, right? And due to the accumulation of this negative charge, there will be electric field like this. So electric field due to plate A, EA will be like this, and electric field due to plate B, EB will also be in the same direction, right? Like this. So this is how we will have electric field inside the or in the space of separation between the plates. You have two plates separated by certain distance now, obviously. So and that distance, the separation of the plates should be filled either by air or kept empty, or it should be filled with certain dielectric. We will see why it should be filled afterwards. But now let us assume it is filled with air now, okay, or kept empty. So the expression for electric field due to this positive charge, okay, you should remember the applications of Gauss law, second derivation, electric field due to a positive charged plane, a positively charged sheet. Okay. So E we had sigma by 2 epsilon naught, right? This is due to a single sheet, right? Remember that? You should remember it properly. So now you have sigma by 2 epsilon naught in this direction inside it. And you see for this due to the negative charge, once again you have field like this. So I can take EA is equal to sigma by epsilon naught in this direction due to this plate EA. And similarly EB will also give us sigma by 2 epsilon naught, right? Because even though this plate is not there, this will have its own electric field EB in the same direction, because it's negative, the electric field lines will go towards the negative plate. So EB is also equal to sigma by 2 epsilon, because sigma is same because the area of the plates chosen is same and the charge accumulated on them are also same, the magnitude, right? So now you have EA and EB with you, which are equal, and the net electric field inside is sum of this EA and EB, right? They are actually the vector sum. Since they are in the same direction, we will directly write them. So electric field, the net electric field in the interspace or the space in the separation of space between the separation of plates, E is equal to EA plus EB, which is equal to sigma by 2 epsilon naught. Sigma by 2 epsilon naught simply becomes sigma by epsilon naught, right? Agree? So now you have the expression for electric field inside the plate. So why do we need them? Yeah, we need them. Wait. So what is sigma actually? Sigma is surface charge density. Should go through the first chapter once. Okay, you'll get to know. The expression for sigma is Q by A, right? Epsilon naught stays there. So this expression for electric field becomes Q by A epsilon naught, where A is the area of either of the plate, or this or this. Okay. So A is the area of the plate. So we have one expression for electric field. Let me call this expression as equation 1. E is equal to Q by A epsilon naught. Now moving ahead, we have a connection or expression which connects electric field and potential difference. Remember that? we took it as E is equal to minus dV by dx. Remember this chapter itself, before 2 classes we derived this. Now we are applying the same condition here, okay, and no need to worry about this negative sign. We are bothered more about the magnitude. So, and this capacitance will be positive, okay, capacitance can never be negative, no need to worry. So, it's about the ability to store charge in it, right. So, that can't be negative physically. So, we will be worried more on the magnitude part. So, it is dV by dx. What is dV? You choose 2 points, okay, and the potential difference between them is dV. So, here the potential difference between the plates is V, simply V, right. We choose it as V for this case, ourselves choose it. So, instead of dV I will write simply V. And what is this dx? Dx is the distance between those 2 points, okay, dV by dx, you go for that and you will get to know that derivation once you go. So, dx is the distance of separation. Now, what I will do, I will take the distance of separation between the plates as small d, simply small d, okay, area is capital A and the distance of separation between the plates I will choose that as small d. And hence I got new expression for electric field from the concept of potential difference. So, E is equal to V by D it became. Let me call this as equation 2, okay. Now, look at them, equation 1 and equation 2, they look similar to us. I mean, we have E electric field same in the LHS. So, put them, equate the RHS part. So, you have V by D is equal to Q by A epsilon naught, right. We are close, very close. Now, let me send V here and A epsilon naught here. So, which gives us A epsilon naught by D is equal to, are we good? Sigma y q by A, yeah, fine. A epsilon naught by D is equal to Q by V, right. Now, come here. What is Q by V? Q by V is C capacitance, which is equal to C, right. That is good. So, finally, we have the expression for capacitance C, which is expressed in terms of the physical conditions of the given capacitor, right. Whatever you have in the expression are like the C is equal to epsilon naught A by D. Look at this, epsilon naught is the electric permittivity of the medium between these plates. We choose air, that is why it becomes epsilon naught. If we have chosen some other medium, it would have epsilon simply, right. You should remember those things, which that is why I stressed these things while solving problems from the previous chapter, right. Should recall them. So, instead of epsilon naught, I should have put epsilon if I had certain medium placed between the plates. Now, no medium, it is simply air. Air is also medium, but air has the dielectric electric permittivity similar to that of vacuum. So, I took that epsilon naught. So, which is a physical part of the capacitor. A is the area of either of the plate, which is also physical one. D is the distance of separation between the plates. Following? So, C becomes equal to epsilon naught A by D. Now, different kind of questions might arise. This is the physical expression for capacitance. We have described it, derived it. Now, you can think, sir, what if I cut one part of the, okay, this is the derivation, okay, whatever I am telling now is a little extra for you, just as a part of curiosity, because so many of you think in a different way, I know that, right. So, what if I cut one of the plate to this much, say half of its original area, then which area should I consider, whether the area of A or whether the area of B. So when you have this kind of situation, normally not asked for boards, normally discussed in competitors. When you have this kind of arrangement chosen, this part above the plate of A or this part of plate A is not also not of use for us. Okay, so this is the area which has to be chosen, shortest area. Okay, following. So that's fine. This is about the derivation of capacitance in terms of its physical dimensions and properties, and this is very important derivation, normally asked for 2-3 mark, 3 mark, and in the coming class we will discuss what happens when we connect, when we put dielectric medium inside it and we connect capacitors in series and parallel. We will discuss all those things. Thank you.